Welcome to this lecture. Over the last couple of lectures, we were discussing about the data flow diagrams. The data flow diagrams are popularly used to do the structured analysis, that is capturing all the functionalities of the system and then doing a top down decomposition of the functionalities. We found that DFD is a elegant mechanism, very simple, and it produces a data flow model of a software, identifies various functions at various levels and the interactions in terms of the data exchange among those functions, and that forms the background or the design document based on which further design can be carried out. Structured analysis is, as you were mentioning, is so popular, not restricted only to the design aspect, but also for many other problems, including in requirements analysis. DFDs are used, but let us find out, are there any shortcomings of the DFD, and that will give us some idea about for what applications DFDs are not suitable and what needs to be done to the DFDs to extend those to be applicable to those areas. Now, let us look at the shortcomings of the DFD model. The first difficulty is that here the functions are only identified by the names written on the bubble, and therefore, it can be very imprecise. Just by looking at the label, we have to infer about what all is involved in the function, and therefore, many things will remain ambiguous, incomplete. Just to give an example, let us say we have a bubble and the name of the bubble is find book position. So, we have find book position as a bubble, but then we can imagine that the find book position, given a book's description, it outputs where it is located in a library, but that is a very rough idea, a rough description of the problem. For example, it does not tell us that how do we describe the book position, how do we give the input, do we give the name of the book, do we give the author of the book, and so on, and also what would happen if the book is not there, what would this functionality do. We are given a book which is not present in the library, and also what would happen if given a book name and multiple entries in the library match same book title, but different authors, or maybe same author and multiple books. Does it display all of them, or does it display one? So, those things are not clear, and therefore, the DFD model, the first glance, is imprecise. Another major problem with the DFD representation is that control flow aspects are not represented. For example, we have this DFD model. Now, in what order does the accept order take the data? Does it take first customer history, then the item file, then the customer file, and then the order, or first it gets the order and then the customer file, and so on. This is especially important in case of real time systems, where the timing issues need to be analyzed. For example, do these two bubbles they execute parallelly or they execute sequentially? If there are multiple bubbles that are connected to this bubble, let us say we have another bubble connected here, let us say pending, determine pending order. So, would this execute first or would this execute first? So, these aspects, these are the control aspects, are not really represented here. We just write what data flows here, maybe some data, book name, etc. So, all are just data exchanges among the different entities, and the bubbles are captured. And that is the reason why timing analysis using a data flow diagram is very difficult, and this diagram has been extended with control flow notations to indicate in what order the processing takes place, and that is for doing the timing analysis. But we will not discuss about those aspects in this lecture series. There are other problems also. One of the problems is that we achieve a functional decomposition at different levels of the DFD, but then there is no guideline about to what depth the decomposition should be carried out. We have only mentioned through a very loose statement that the decomposition should be carried out until we reach a function which is very simple, but then that is a vague statement. What is function is simple to one person may not be the same for another person, and therefore, different designers can carry out decomposition to different levels. Another problem is that for different designers, they can come up with very different DFD representation for the same problem, and also many times we do not have any way to tell which DFD representation is superior, and therefore, we have to explore multiple DFD representation. Okay, already seen that how to decompose, that is not clear. We just say that see bubble should be decomposed in the next level, take one bubble from a layer level and then decompose it, but then we never said how to decompose it. We just said that look through the activities that are to be carried out by that process or that bubble, and then identify the sub activities, and those sub activities become the processes or bubbles in the next level, but then that is subjective, because different designers may come up with different sub functions, and they will come up with different DFD representations. But in any case, DFD is a very useful technique, very easily learned, and once you learn it, you will find it comes to use not only in software design, but in many other areas. In software development, for example, in testing and so on, and also in non software development areas. There are many tools that are available using which you can develop the DFD model. It simplifies the task of developing the model and produces good diagrams. There are several commercial tools which are popular, for example, Visio, SmartDraw, which includes a 30-day free trial, eDraw, Creately, Visual Analyst, and so on. And there are some free tools like Dia, which is a GNU open source tool. Please use some of the tools. You will find that the tools are extremely easy to learn, and based on the concepts we discussed, can just start using the tool. The download is very fast. For example, Dia, and typically we have pick and paste the different DFD symbols would be there as menu items. You can just pick them and paste wherever necessary, and draw the data flow arrows between bubbles. So, and almost every tool, they develop the data dictionary as you develop the functional model. But then would like to give a simple caution that the concepts are more important. Understanding what does DFD model, how does it model, the hierarchy, balancing, and so on. But if you ignore the basic concepts, but just spend time on the tool, just trying to master the tool without knowing the basic concepts, it may be counterproductive. If you are hoping that just by learning the tools well, you will become a good designer, then your hope will be misplaced, because just to give an analogy, that let us say you want to become a famous writer of a thriller stories, and then let us say you learn the word processing package very well, that will not make you the writer of thriller stories, a good writer of thriller stories. What you need is how to write thriller stories, the storyline, and so on. Just learning the word processing package is not, does not lead you, or does not automatically make you a good story writer. The same way, just by learning the structure analysis and structure design tool, you do not become a good designer. You need to understand the concepts well, and of course, you need to practice with several problems, and that will make you a good designer. Now, once the data flow diagram model is complete, based on the model we develop the design, the high level design, and we call the process as the structured design. The structured design, it takes the results of the structured analysis and it transforms this structured analysis into a structure chart. So, if this is our set of DFDs, the DFD model, as you are saying, is consists of a set of data flow diagrams, the root level, level 1, level 2 diagrams, and so on. Through structured design, we transform the DFD model into a structure chart. So, we will see the methodology by which, by analyzing the DFD model, we will be able to come up with a structure chart. We will give some methodologies, that is the structure design methodology, using which you can transfer the data flow diagram into a structure chart. And in the structure chart representation, we will have the different modules of the system, the module dependency, which will be represented in the form of arrows, and also we will represent the different data items that are passed between the modules. So, this is an example of a structure chart of a problem, and we will have, these are the modules of our design, and for each we will write a module in the code. It represents the call relationship between two modules. So, the root calls all these three. We will also represent the data flow that occurs between the different modules through some notation. We will see, we will write the name of the data D1, D2 and so on. Now, let us see what are the elements of the structure chart. The structure chart identifies the module structure, and we can easily program the structure chart. It is actually the high level design, and in the next step, based on the structure chart, we do a detailed design, where for each module we identify the algorithms, data structures and so on, and that is directly transformed to code. So, here in the structure chart, we only represent the module structure, what are the modules, what is the call relationship among the modules. So, these are the modules, the different modules M1, M2, M3 etc., and the call relationship among modules and the data exchange among modules, but we do not represent in the structure chart what exactly happens in M2, what is the procedure or the algorithms used in M2 or M3, that we do in the detailed design, where we identify the algorithms, the data structures that are used, and we develop a module specification for each module. So, let me just repeat that part, that the structure chart representation is called as the high level representation, the high level design, and based on the high level design, we carry out the detailed design, where for each module we develop a module specification, which contains the data structures that are to be used in the module, and also the algorithms that would be used in this module. Now, let us see what are the basic building blocks of the structure chart. Of course, the central part of a structure chart are the modules. The modules are rectangles, and the name of the module is written, very simple, that we draw a rectangle for each module, and we just write the name of the module on the rectangle. The second element of a structure chart is the arrows. the arrow represents the invocation relation, that is which module calls which module, and when there is a call from one module to another module, then the control is passed from one module to the other. So, if root calls process order, then the control is passed from root to the process order, and then once the process order completes, the control is back with root, and then it may call handle indent and then the handle query. But then this sequential aspect, whether it will call first this one, next this one, third is the handle query, it is not really represented here. So, this just says that they are called, but the order is not indicated here. It may first call handle indent and then may call process order and so on. The third item or the third element is the data flow. So, we represented here the data flow aspect. We draw a arrow here on this invocation showing the direction of the data flow. So, what this represents is that the root calls the process order and the process order gives back the order to the root. Very simple notations. Now, there is one more element in the drawing of the structure chart, which is the library module. It is a module actually. So, it is a rectangle, but then we just draw these two parallel lines here, and this indicates the ones that are made into library. Some of the functions are called frequently by other modules, and to represent that these are the library modules, we just draw them in this notation. There are few other notations, for example, selection. So, draw a diamond here, we draw a diamond here and it indicates selection. So, it will call one of the module depending on some decision here. One more element here is the repetition. On the invocation arrow, if we draw an arc shaped arrow here, that indicates that these modules are called many times. In a loop. Now, the structure chart, there will be only one module as the root, and then there are control relationship between two modules if the module invokes the other module, and based on the methodology that we give and also any structure design methodology, we always come up with a structure like this. It is a tree like structure. These are arranged in levels. But then we do not have a lower level module calling a higher level module. We do not have this kind of arrow here. So, there is the control relationship from one module to the next level of module, but we cannot have a module calling a higher level module, This is an example of a bad design. We had discussed while discussing about the good characteristics of design, said that the design has to be layered, and a higher layer module can call a lower layer module, not vice versa. We will see how the design methodology that we discuss, it will give us it will automatically result in a layered representation or a layered design, and there is no back arrows in that. If you are by chance while applying any methodology, you come up with arrows which invoke the higher level modules, mostly that is not a good design, unless there are some exceptional situation. It does not, it indicates that it is a bad design, and we have to be careful. The main reason why the lower level design modules should not call the higher level modules is because of the principle of abstraction. This we had also discussed earlier, that due to the principle of abstraction, at any time we are concerned about only some modules. We do not have to get concerned about all the modules together, and if our module structure is a tree like diagram, if we look at these modules, bottom level modules, then we do not really are concerned about the upper layer modules, because the results are produced solely by these modules based on some data that is passed here. But just imagine that if we have a back arrow here, so this will violate the principle of abstraction, and lower level module is calling a higher level module, and therefore, understanding this design will be difficult, because when we try to understand this one, we see that we need to understand the one that it calls, and then we need to understand the one that it calls, and we will end up just going round and round, and same thing happens while debugging. An error, if there is a failure, we are trying to debug and find which module has the error. We see that we are looking at all modules round and round, and we will have difficulty in debugging, in understanding, and so on. And therefore, the layering of the module, it is an instance of the principle of abstraction, and helps us to develop a design which is easily understandable, and we can easily debug that. We are almost end of this lecture. We will stop here, and we will continue in the next lecture. Thank you.